Welcome, dear PyFrac users. This is a short introduction video on the minimum input file, so the minimum data you need to provide to perform a radial simulation with an injection history. And we will simply show you how to do that and which parameters to provide and what they mean. And as such, then you can go and launch your simulations very easily. So if you see this video and you do not yet have installed PyFrac, then I refer you to our GitHub and to the channels where we inform about everything that is going on around PyFrac, because that's not going to be part of this video. So for this video, you need to have PyFrac installed and up and running. So what you see in the background is my PyCharm editor. So PyCharm, that's just an interpreter. So that's a Python interpreter. You can use whatever you want as your Python interpreter. Everything that I will show you in the next few minutes is applicable on any Python interpreter you use. You just need to have PyFrac installed and you need to have it running. And then you can also run everything from the shell. This will also not be part of this video, but there is also the information on how to do that. That can be found on our GitHub or via our information channels. So what we will treat now today is, when you see here on the left, that's the structure of PyFrac. We have within examples, we have the example on a simplified input. So if I go to this example, the example of a simplified input, then you are simply seeing what I see now. So I'm going to close again here on the side just to have it a bit more easy to read. So the head is always the same. You see directly who was the persons were that did provide this file. So you can also go directly to the correct person if you have questions on our information channels. First of all, we have some physical parameters that you need to provide. So sigma 0, that's the confining stress, and I'm going to say that now, and I'm going to say it a lot. Pay attention, because all the things you input are in standard SI units. So here we have a confining stress of 1 megapascal, so we need to put 1e6 because the standard unit is Pascal. So that's just our background. You can change this value simply by you leave the name, leave the equal sign, and just change the number on the right-hand side. Then we have a Young's modulus. That's the Young's modulus of the solid, because here in that part we will treat the solid, even though sigma 0 is not really a property of the solid. Same as the Carter-Slikov coefficient, we regroup that as solid. Young's modulus and Poisson's ratio. So everything you might need, which is like shear modulus or plane strain modulus, will be calculated by PyFrac directly. So you don't need to give that as an input. You can simply give us here Young's modulus and Poisson's ratio, which are two values which are fairly common to provide for rocks or for your medium. Then we have the fracture toughness. Again, here, pay attention. It's Pascal square root meter. It's the standard unit that fracture toughness have. So if you have 1.5 megapascal, as in our case, you simply use 1.5 E6 because it's a Pascal and you want to have megapascal. Density of the solid, kilogram per cubic meters, and then Carter-Slikov coefficient. Carter-Slikov coefficient, so PyFrac uses the Carter approximation for Likov. This coefficient, you can find it in the literature, and it's a function of your fracturing fluid and everything. So you can provide an estimation of Carter-Slikov in here. Then you have the fluid. The fluid, we choose to use water. So you have the dynamic fluid viscosity in Pascal seconds, which is mu. 1e minus 3 for water. You have the density of the fluid, which we provide down there, and then we come to things that are related to our injection. Now, the things that are related to our injection, that's maybe something which is a bit more interesting to talk about. So I'm going to do some drawings about that. Let's just assume here on the top, I'm drawing two axes in black, where we have one, that's the time, and y-axis, that's q0. Now, what do these variables mean? I'm going to tell you first that t change. So the first value that you have here, that's all the times within the simulation where you do a change to the injection rate. So PyFrac is based on block injections. So we inject for a certain rate during a certain time, then we change the rate for the next block of time, and so on and so forth. And every time we change, well, that's when we have one of these numbers. So this is in seconds. So here we will change after 1 minute, then we will change after 1 minute 40, and at about 2.5 minutes, a bit more, we will change a third time. Now the first entry is always needs to be 0, 0 because our fracture simulation starts at 0, 0, and at 0, 0, thus you have a change in injection rate because you start injecting. So that's what T change is. Then you have Q0, and that's the corresponding injection rate. Now let's exactly take the example here. So at 0, 0, we have a change to 0.01. So if we now go to what we see on the right here on our graph, then at 0, 0, so that's 0, we change here to 0.01. That's our injection rate. Then this injection rate goes on until we have our 60 seconds, which is the next time when we change. So at 60 seconds, there's the next change. And at 60 seconds, we drop to the corresponding value, which is down there. We drop to 0. So that's basically this. Now we have a block injection. So that's one block that we have. That's basically our first block of injection. Then time goes on, and at 100 seconds, we change again. This time, we have a slightly higher injection rate. So this time, injection rate goes up to 0.015. Now this goes on until we change again. So the last time we change is at 160 seconds. Gonna plot it there, 160 seconds. And at this time again, we drop to 0, such that we have a second block that we inject. And now, as nothing more is provided, it will just stay at 0 forever. So at some point the fracture will arrest, but there's no more injection going. That's the principle, and this also means that you must have, in fact, the number of elements in Q0 matching the number of elements in T change, and then it's always the value at point I of Q0 is applied between I and I plus 1 of T change. So the number of elements needs to match. The first element is always 0.0, and it's always the block in between that this rate is applied. If you want to have an injection, I'm gonna draw that in green. If you want to have an injection that starts at 0 and then just goes on until infinity with a certain rate, let's suppose 0.0125, what you would do is simply you take Q0, then you make an equal sign. You don't do a list as it is provided here, but you would simply write Q0 equals 0.0125 as a float, and that's it, and then you would never stop. Next thing you need to introduce, in fact, in your script is an initial radius. So what you will introduce here is an initial radius. The fracture will have a residual, a minimal hydraulic opening, and it will be at a minimum pressure, just that it is just open to sustain this minimum opening, in fact, and you will provide that for a given radius. So the only thing you need to give us is the radius, and then everything goes on. Pay attention that radius is again SI standard unit, so it's in meters. So here we would have 5 centimeters of radius. And then the next thing is the domain limits. And for the domain limits, I'm going to start already the simulation so you can see directly what this means, what these limits are. So if you want to debug the simulation with PyCharm, it is this little bug here. If you want simply to run it, then it would be the run sign here. So I will now simply run it because it will then go on at the side. I will already run on the top there, and I will go on explaining you everything that is in thing. So to run it, I simply tab over there. You see already down here some information popping up, which I will talk about soon. So we see now, well, that's what is plotted. It's the fracture opening, and as I said, well, red, that means it is closed, but it is close to this minimum hydraulic width. And we see now that the injection is starting on. So what are the domain limits? Well, it's X and Y. Our injection point is at 0, 0. So the first entry is what you have here. It's the minimum in X minus 0.1. Then you have 0.1, that's the maximum in X, and same for Y, minimum in Y, maximum in Y. So you see here, that's basically the square domain you have over there. You're not limited to square domains. You are limited to rectangular domains, but it's also that the domain must not be centered at 0, 0. It's just that the default injection point is 0, 0. So if your injection point is outside of the fracture, or if you have the injection point and the radius then would go outside of your domain, well, at that point, you cannot initiate the fracture because then you cannot simply discretize. The number of elements, that's the number of elements you have in this domain. So between minus 0.1 and 0.1. So there are 61 elements in X, that's the first entry, and 61 elements in Y, that's the second entry. So on that, we recommend you not to use something which is smaller than 41 on 41 elements. Why? That's simply because of the numerical precision of PyFrac. On the other hand, we don't recommend to use number of elements which go far above like 100, because if you go above 100 times 100, then a time step takes extremely long. And if this happens, well, that's just restraining your calculation time. We have a second thing, which is the time discretization, and this is optional. So you've seen here the time, it's plotted down there, it's 1e minus 7. So there's an automatic time stepping scheme included into PyFrac, but you have some liberty on adapting it as you want. So the first thing you can do is fixed times. You don't need to do that, but you can do that. And fixed times means simply that if the fracture by the automatic time stepping would jump, for example, you were 30 seconds, so you are at 29 seconds, the time step it want to take is 10 seconds, so it would go to 39 seconds, then PyFrac will say, no, you fixed the time to 30 seconds, so it will do in 29 seconds, then 30 seconds, exactly because you wanted the solution at 30 seconds. It will store the solution, which is also not the base case. So it could also say you don't want to save every time step. You can save several time steps. That's not part of this video, but for that, you can go onto our webpage to get the information on that. But then for sure, at this time, it will not only do the simulation at exactly 30 seconds, it will also save it. Same for 75 and 150. You will see that if you follow the simulation, which is running on the right during this time. Another thing you can provide is a maximum time step. So the time step is adapting, and it's in a power law adapting basically. So it gets bigger and bigger and bigger and bigger with fracture propagation. And in that sense, you can provide a maximum. So you can also say, I don't want my fracture to do a time step that's bigger than 100. If you want that, you simply type here 100. As long as you type NP infinity, that means the maximum time step is infinity, so you don't restrain your time stepping at all. Now we go back to some simulation specific things. Well, the first thing is the simulation name. So we need to give your simulation a name as to get information back from it and so on. The simulation name, I simply name it sample simulation here. You can type whatever you want as a string or a series of characters. That doesn't matter. Then you have a save folder. So where should this simulation be saved? And that's what you provide here in the relative path. The dot data means it's in the path where you have your file. Then you will get what is going on. So how does this look like? Well, we have examples, data, sample simulations, data sample simulation. That's simply the folder. Then if you go into there, well, you see that's the simulation. That's the simulation I started 1626. I started it at 1621. So you have the name that you provide in simulation name, and then you have date and starting time. So why do we give you date and starting time? Well, if you have two simulations with the same name, you don't want necessarily them to override each other. Or basically you don't want them to override each other because maybe you had a parameter which you got wrong or you had to adapt something. So you want it to have separate. That's why we also provide the starting time like this. You don't override your stuff and you can distinguish between different simulations. Another thing which you can provide or which you should provide is the final time. So we see here time is going up. Now we are at 7 minus 6. Then the time goes up, and I say here at 2E3, so at 2000 seconds, you stop the simulation, because from that point on, I suggest there's nothing more happening, or there's nothing happening anymore that is interesting for me. So at that point, we stop the simulation. You can also put this time extremely high and then just wait and end your simulation manually if you're more comfortable with that than by doing it in that way. We have a gravity flag. Well, it's pretty self-explanatory, but if you have it to false, then we do not take into account gravity. However, if you put it to true, then we will take into account gravitational forces. So that depends on the problem you have and on what you want to investigate. We have two different booleans that simply to facilitate for you what's going on and also how to treat then the second part of this this short tutorial. So you have run the simulation, which is simply the question, well, do you really want to do the simulation? Because as you see on the left, the simulation data gets stored. So once it is stored, you can also only do post-processing. So if you only want to do post-processing, you set run simulation to false. For sure, you need to have run a simulation with the name in simulation name, because what it will do if you put it to false here, but you let the post-process be on true, this means it will take the last simulation you've done, so the last one you started, the most recent simulation with the name in simulation name, which is placed in your save folder. So in that case, that would be this simulation that I started over there. And then it will do post-processing with the data, which is within this simulation. If you put both to false, then simply nothing will happen. And if you put the simulation to run true and the post-processing to false, you will run the simulation, but you won't post-process it. That's also something you might be interested in. Just already run the simulation, post-processing, I will do it afterwards. So just keep post-processing out of it. The next part of the code, that's the code where basically you run the simulation. We hide that from you, doesn't need to bother you. So for your radial fracture, the minimum information that is required is what is within here. That's all you need to know. If you want to go into details, we will do different tutorials and so on. Then comes post-processing, and post-processing is not part of this short video. So there's a colleague of mine which will present another video on that. So as we now already have seen, our fracture, which was closed in the beginning everywhere, where you just had the hydraulic opening, is now continuously from the center. It opened and it spread outwards. And at some point now we will reach the boundary, then the fracture will effectively start to propagate. I will let this fun to you. So just run the simulation, see what happens, and in about like 3 time steps, we will propagate from what you see. Thanks very much to all of you for listening to this short video. I hope you have lots of fun with our code PyFrac, and see you soon. Bye.